5.1 Day 2 Randomness, Probability, and Simulations. After today's lesson, you should be able to design and perform a simulation. A simulation is an imitation of chance behavior based on a model that accurately reflects the situation. Here are some steps to set up a proper simulation. First, you need to look at what is the question of interest about some chance process. For example, let's say I'm trying to find out if I'm going to have a boy or a girl when I have a baby. The plan. Describe how to use a chance device to imitate one repetition of the process. Explain clearly how to identify the outcomes of the chance process and what variable to measure. For example, if I'm trying to see if I'm going to have a boy or a girl, I could use a coin, and I could let heads be a boy, tails be a girl. I could also use a die. I could roll the die and let the even numbers represent a boy and the odd numbers represent a girl. Or I could use the number digit table in the back of the book and let the even numbers represent a boy and the odd numbers represent a girl. I want to perform the repetitions of the simulation and then make a conclusion. Use the results of the simulation to answer the question of interest. Again, we can use physical devices such as a coin, dice, you could use a deck of cards, or the random number table in the back of the book, which is table D. Also, you could use your calculator to perform the simulations. Here's an example from page 290. In this situation, a local high school that has 95 students that have permission to park on campus. Each month, a student council holds a golden ticket parking lottery at the school assembly. The two lucky winners are given reserved parking spots next to the school's main entrance. Last month, the winning tickets were drawn by student council members from AP Statistics class. When both golden tickets went to members of the same class, some people thought the lottery had been rigged. There are 28 of the 95 students that can park on campus in this AP Statistics class. Design and carry out a simulation to decide whether it is plausible that the lottery was carried out fairly. I'm going to use table D in the back of the book to set up the simulation. I'm going to label the AP students from 1 to 28 and the other students that have permission to park on campus as 29 to 95. Notice I'm going to skip numbers 96 through 00. If I refer to table D in the back of the book and I read across row 139 and look at pairs of digits, because I have two-digit numbers, and record whether or not both winners are from the AP class, I can see here in my first setup I draw 55 and 58. Both were not AP Statistics students. Next, 89 and 94, followed by 04, 70, and then 70 and 84. In the fifth simulation, you will notice that the numbers are 10 and 98 I must skip, and then I have 43. If I continue to carry out this simulation many times, I can see of the times that I did carry this out, 3 of the 18 repetitions, both students would have been from the AP Statistics class. 3 divided by 18 ends up being 0.1667, or about 16.67%. So based on the 18 repetitions I have in this simulation, both winners came from the AP Statistics class about 16.67% of the time. Here is another example of a simulation. In an attempt to increase sales, a breakfast cereal company decides to offer NASCAR promotion. Each box of cereal will contain a collectible card featuring one of NASCAR's drivers: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. The company says that each of the 5 cards is equally likely to appear in any box of cereal. A NASCAR fan decides to keep buying boxes of cereal until she has all 5 drivers' cards. She is surprised when it takes her 23 boxes to get a full set of cards. Should she be surprised? Design and carry out a simulation to help answer this question. This time I'm going to use my TI-89 calculator to carry out the simulation. That will be the device that I use. I'm going to label the drivers as 1, 2, 3, 4, and 5 as shown here. And again, I'm going to use my calculator. So on the home screen, I'm going to go to Catalog and then F3, which is the Flash app, and I'm going to use the random integer generator to simulate this. So when I hit the random integer button, I'm going to enter 1, 5 to simulate buying one box of cereal, and look at each card that's inside. Keep pressing enter until I get all 5 of the labels, 1 through 5, and record the number of boxes we had to open. So on my first simulation, I ended up with a 3, a 5, a 2, a 1, a 5, a 2, a 3, a 5, and a 4. So it took me 9 boxes to get all of the numbers from 1 through 5. On a second trial, it takes me 15 boxes to make sure I get all 5 drivers. On a third simulation, it takes me 10 boxes. If I continued to do this and made a dot plot of how many trials it would take for me to obtain all 5 drivers, it may look something like this. From this dot plot, we never had to buy more than 22 boxes to get a full set of cards, and this includes 50 repetitions of our simulation. Our estimate of the probability that it takes 23 or more to get the full set is roughly a 0% chance. Quick review of section 5.1, randomness, probability, and simulations. In this section we talked about a chance process has outcomes that we cannot predict but do have a regular distribution in the long run. The law of large numbers says that the proportion of times that a particular outcome occurs in many repetitions will approach a single number. The long-term relative frequency of a chance outcome is its probability between 0, which means it never occurs, and 1, which would mean it would always occur. Short-run regularity and law of averages are myths of probability. A simulation is an imitation of chance behavior and can be carried out through the use of playing cards, a coin, dice, a number table, or technology. In the next section, which is section 5.2, we will actually get into the probability rules and perform some calculations.